We want to determine what is the electrode potential or EMF of a cell when tin, it looks like it's being oxidized, it's losing 2 electrons, and lead-2 is being reduced. Its charge is going from +2 to neutral, so that's reduction. It's becoming more negative. Its charge is being reduced. Oxidation always happens at the anode. Reduction always happens at the cathode. The anode is always on the left, the cathode is always on the right in this notation. So if we were to look at the table in the textbook of the standard electrode potentials, we would see tin 2 plus 2 electrons. It's always written as a reduction reaction showing the oxidizing agent on the left, and lead 2 plus 2 electrons. Tin going to tin naught, the element, and lead 2 going to lead naught, the element. Now that's not necessarily what's happening here. Lead 2 is going to lead naught, but tin is being oxidized. But the reactions in the book are always written as reduction. So this is going to be our anode. It's minus 0.14. And this is going to be our cathode. That's minus 0.13. So you can see that tin 2 is a slightly stronger oxidizing agent than lead 2. Tin 2 is, we could say, a little bit more hungry for electrons than lead 2. So that means that lead naught is going to be a reducing agent that's produced. It's going to be the weaker reducing agent. All right, so let's take a look. We want to calculate E of the cell, but we need to calculate E0 of the cell. E0 would be the voltage if everything was 1 molar, and it's not. So let's just calculate that. E cell is E0 of cathode minus E naught of the anode. Okay, again, this is my anode, this is my cathode. So we're going to subtract negative 0.13 volts minus a minus 0.14 volts. That's going to equal 0.01 volts, which is certainly not a large EMF or electrode potential for this particular cell, but it is because they're so close on the table. All right, now that would be 0.01 volts if everything was 1.0 molar. It's not. So we have to calculate the electrode potential for this particular cell, and we start with the electrode E naught of the cell under standard conditions. And then we have a correction factor, which is 0.0592 divided by the number of electrons exchanged times the log of Q. Now, let's label this equation. This is the Nernst equation. Very important, needs to be remembered. And we've already calculated E naught of the cell. Remember that Q is our quotient, similar to calculating the equilibrium constant. It's going to be the concentration of the products. Anything that is in solution or any gas, we would write the pressure over the concentration of the reactants. And that would be to the power of any subscript. And we don't have, coefficient. We don't have a coefficient in this reaction because it's balanced. We have 2 electrons on being exchanged, and both are +2, so we don't need any coefficient. If we were to balance this equation, we would get something like this. So we can see that we're balanced with respect to electrons, with respect to the atoms. So there's not going to be any coefficient. All right, so Q is going to equal the concentration of the products. The only product is tin 2. That's the only thing that's in solution, and lead 2 is going to be my reactant. So we want to make sure we get this right. So my product is going to be tin 2. Even though it's over here on the left, that's what's formed. And so that concentration is going to be 1.00 molar. That's what's given. And then on the bottom is going to be my lead 2, 0.0010 molar. Those are the only species in the reaction. Tin knot and lead knot are not going to be included in that. So that's going to equal 1,000. Log of Q equals 3. And so when we plug this back into the Nernst equation, you can see that N is going to equal 2. So let's plug this all in. And we get E cell equals, E naught of the cell was 0.01 minus 0.0592 over 2, and log of Q is 3. So we've already factored that in. So that turns out to be 0.01 minus 0.089. So the potential of this cell turns out to be negative 0.0788 volts. Because our concentration is so low on the reactant side, it shifts the equilibrium back towards the reactants. We're negative, and so this would not be a spontaneous cell reaction at all.